Salam and welcome everyone. So today we're going to be doing a question on the screen that says a sample containing or consisting of 1.0 mole of perfect gas atoms for which CVM, which is the molar heat capacity, equals 3 over 2 of the gas constant, hence 3 over 2 R, initially at P initial equals 1.00 atmospheres, and also T initial, meaning the initial temperature is 300 kelvins, is heated reversibly to 300 Kelvin at constant volume. Calculate the final pressure, the change in energy, the heat, and the work done. So the first thing you have to do when you're working with a question like this is for you to first of all write out the parameters. We're told that we have 1 mole of the perfect gas. So the number of moles is 1.00 mole. We know that the molar heat capacity, CVM, equals 3 over 2R. We know that the initial pressure, so P initial, where it's here, it's denoted P1. You can also say that P1, P2, or PI, PF. So P initial, P final. That's what I'm going to be using in this particular question. So that one is 1.00 atmospheres, and the temperature, the initial temperature, is 300 kelvins. Now, we're told that this is just like the beginning of the reaction, but there is increase in temperature. So basically, the sample is heated reversibly. So that means the final temperature, because there's heat applied, is going to be more. So, I mean, we're told that that is 400 kelvins. And then all of this occurs at constant volume. So the first thing you have to know is this. We are asked to find the final pressure. But before we do that, we can determine um, some information from this question. You see, we're told that this is happening at constant volume, and usually the general formula for work is negative P change in V. Well, because this is occurring at constant volume and the volume is the same all through the entire process, the entire reversible process. Well, since there is no expansion, there's no change in volume, what you're going to end up with is a zero because the change in volume is zero. I'm sorry, the constant volume will make the change in volume zero. The work is going to be equal to zero. So that's one thing I need you guys to know. So we've gotten the answer to one of the question. But then we have to remember that we have internal energy change in U is usually equal to Q plus W. So the change in internal energy is heat plus work. We already know that work is going to zero or is equivalent to zero. Hence, the internal energy change in U is going to be equal to just heat by itself. So I wanted you guys to know that. So now we have successfully answered one question, which is W. So when we determine what the value for heat is, we're going to also note that that value is equal to the change in internal energy. But before we go on to solve for heat, we can work on this question, right? Because we're asked to find the final pressure. Well, since this is an initial volume, sorry, this is an initial pressure, final pressure type of question, we remember that first of all, the ideal gas equation is PV equals nRT, right? And N, so number of moles is constant, gas constant is constant, and volume is constant. The only things that have a change in value, meaning the initial and the final have different values, and the initial and the final is basically not the same, is the pressure and the temperature. Hence why we have an initial pressure and a final pressure and an initial temperature and a final temperature. So what we're going to do is that we're going to put PT in one side of the equation and put the constant information on the other side of the equation. So when we do that, what we end up with is P divided by T equals NR divided by V. So if you do your math very well, this is what you're going to get. All this information is constant. And you're going to see the reason why I'm writing this down step by step. So all of this information is constant. You're wondering, okay, what is the point of this? Well, the point of this is because we know it's constant, meaning every single time, every single moment in this entire process, the nr divided by v is going to have a constant value. Hence, the initial, so p initial divided by t initial is going to have the nrt constant, this entire thing to be constant, and p final divided by t final is going to have nrt as a constant information. So what we can do now is to merge two of them together. So we end up with P initial divided by T initial equals P final divided by T final. So P final divided by T final. So this is what we are going to actually use to solve the question. So all we have to do is just input the information. We have the P initial. We're told that that is 1.00 atmospheres. So we can just say 1.00 atmospheres divided by T initial. So initial temperature is 300 kelvins. And then P final here divided by T final. So the final temperature. So that's the final temperature, which is 400 Kelvin. So yeah, that is what's going on here. So one thing we can do is we can just simply cancel out Kelvin since we're actually solving for P final. And when we do P final here, we can just simply cross multiply this, and what to end up with would be 1.00 atmospheres times 400, okay, divided by 300. So basically we cross multiplied and we did the information in terms of just PF. So when we do that, of course, we cancel out this. So this will be 4 here, this will be 3, and that will be P final is going to just simply equal it's going to just equal 4 over 3 atmospheres, which is the same thing as 1.333 atmospheres. But then let's go back to the question in order for us to see how many sig figs. 1.0 is 3 figs, sig figs. 1.00 atmospheres, 3 figs, 6 figs. 300 and 400 kelvins are also in 3 sig figs. So we're just going to put this answer in terms of 3 sig figs. So P final is actually going to be 1.33 atmospheres, and that is basically the answer to this question. So the next part of this question is that we're supposed to determine heat, right? Before we do that, let's not forget that heat is the same thing as change in U, because of course work is equal to 0. So what this is telling us now is that we're going to determine heat. So that would be heat at constant volume is equal to CV, comma M times number of moles times the change in temperature, right? Times the change in temperature. So times the number of moles times the change in temperature. So this is basically the formula that we're working on right now. Sorry, not that we're working on, that we're working with right now. So the molar heat capacity times the number of moles times the change in temperature is going to give us what the heat is at constant volume. So all we have to do now is to just input all of the information into the equation. We know that according to the question, the molar heat capacity is 3 over 2 of the gas constant. And the gas constant, by the way, is denoted as R. And the gas constant for this particular question, don't forget that the unit for heat is in joules, right? So that's just basically 8.3145 joules, right? Per mole Kelvin. So that is what the gas constant is. Since we're dealing with the CVN, and that is telling us that this is equal to 3 over 2R. So we're just going to say 3 over 2R, which we're going to input here as 8.3145 joule per mole Kelvin, okay, times the number of moles that we're given, which is 1.00 mole, okay, times the change in temperature. And we know that the initial temperature is 300 Kelvin and the final temperature is 400 Kelvin. So that's TF minus, T final minus T initial. So that would be 400 Kelvin minus 300 Kelvin. So this is basically how you do this question. So QV here is just going to be 3 over 2 times 8.3145. But before we go there, let's start canceling out the units. Let's cancel out the moles. Let's cancel out, we can't cancel anything out again because we need to subtract 300, from 400. But let's just work with what we have for now. We have 3 over 2 times 8.3145. So we have 3 over 2 times 8.3145. So that would be 12.4718 joule Kelvin, okay, times 1.000 times 400 minus 300. So that would be 100 Kelvin. So you cancel out the Kelvins and you see that 12.47175 times 100 equals 1247.18 joules. So this is basically the answer that we are getting. But the issue is that we cannot put this in chemistry, mainly because we have to put things in the number of significant figures that is proper. So we're going to go back and see how many sig figs is in this question, just like we did for the final pressure solution. We see that it's 3 sig figs that we're supposed to use. So we're just going to answer this question up until 3 sig figs. So that would make this the heat at constant volume to be 1.24, but then we have the 7 here, so we're going to approximate. So that'll be 1.25 times 10 to the power of 3 joules. And this is the heat at constant volume. And of course, since work equals 0, the internal change in internal energy is going to be equal to Q. So hence, change in internal energy is going to also be 1.25 times 10 to the power of 3 joules. And that is how you answer this question. If you have any questions, please put it in the comment section. If you have any suggestions, also put that in the comment section. I'm an online tutor for students who want to succeed. So if you're a student that is looking to get an A in all your STEM related courses, make sure you reach out to me at shohabitutoring@gmail.com. I'm an online tutor and mentor for high school, middle school, and college level students, and I help you through your entire school experience to be the best that you can be and to ultimately be a productive member of society. So I wish you guys all the very best. Good luck in your classes, and assalamu alaikum wa rahmatullahi wa barakatuh.